Hello everyone, welcome to another section of the lecture series on measure theoretic probability. So today on lecture 4, we will be talking about the Lebesgue measure. And this Lebesgue measure will be defined on a field and later on be extended to the sigma field generated by that particular class. Whenever we talk about the sigma field generated by a certain class, we want to include some countable unions. What I mean by countable union is that if you have a1, a2 up to infinity, then it implies that the union of their infinity should also belong to that class. When you talk about the field, it implies that if you have a1, a2 up to an, then their union, the finite union, should also belong to that class. So that's the difference. But here we define the lambda, the Lebesgue measure, on a field. So let's take an example. So the Lebesgue measure on the unit interval. So here we consider a unit interval. So this unit interval is from 0 to 1. So let the whole space be this unit interval. And let's build some class or subset out of this unit interval. First of all, the first class we'll be talking about is L. So this L is it's a subset of omega, whereby these subsets are the half open, half closed. So we have A and B, whereby AB lies within the interval of 0 and 1. And we union this class with with the empty sets. Let's consider another class, beta naught. And this beta naught is the class of finite unions of finite union of the joint elements of L. Note that beta naught is a field. Okay. So now we define the set function, that is the Lebesgue measure on beta naught, as follows. That is, the Lebesgue measure on the empty set is 0. The Lebesgue measure on the empty set is 0. And if A belongs to the class L without the empty set, this means without the empty set, then A is equal to the half open, half closed, that is AB. And the Lebesgue measure on this kind of interval is the difference between the points, their points, that is B minus A. So when you define the Lebesgue measure on an interval, is the difference between them, that is B minus A. Now let's go to beta naught. If A belongs to beta naught, note beta naught is the finite union of the joint elements of L. So if A belongs to beta naught, then you can write A to be the finite unions of some A case, whereby this A case belongs to L, and define a Lebesgue measure on it. So you write A to be the finite union of this A case, and we define the Lebesgue measure on A. So A, the Lebesgue measure on A is equal to the Lebesgue measure of the finite union of this A case, and this is equal to the finite sum of their individual Lebesgue measures. We can write this because note the A case are the joints, and you can actually write this. This implies that A1 intersection A2 is equal to the empty sets. So we can actually write this. So this is the first part of the lecture. Next, note there are many representations of A as a union of the joint elements in AK. So if you pick an interval, you can represent it as many times. So you don't have a specific representations of these AKs. Okay, so you have to take note of that. Now we define another class, B, beta, which is equal to the sigma field generated by beta naught. So we will call beta the Borel cells on on omega. That's the unit interval from 0 to 1. So by Karateodoris extension theorem, we can extend the Lebesgue measure lambda to a probability measure on on B, on beta. Now beta includes some countable unions. That's the only difference between the beta naught and the beta. Beta naught was only for finite unions, but here beta is some countable unions, whereby we want to extend the Lebesgue measure from beta naught to B. So We call beta the Borel sets on the unit interval, and we call this measure the Lebesgue measure. Now, note one thing you have to note: there are subsets of what, of the unit interval which are not in what, in beta. So there are examples of sets for which we wouldn't be able to actually what, measure them, but these subsets are in this what, in this unit interval, but we do not include them in what, in beta. The reason this implies that if you consider the power sets, we cannot extend the Lebesgue measure to the power set because the power set includes all possible subsets of this. So the beta here is a class for which we can actually extend what, the lambda to it. Second thing to note, the Lebesgue measure on R is not a probability measure. Note, for Lebesgue measure lambda to be a probability measure, then the measure of the whole space should be what, to be 1. So if you consider a space that is from 0 to 2 and take the Lebesgue measure on it, note that the Lebesgue measure on an interval is the difference between what, their endpoints. So that is 2 minus 0, which gives you 2, which is greater than what, 1. So we don't extend, we don't actually define Lebesgue measure on R and let it be what, a probability measure. But a Lebesgue measure on the unit interval is what, is a probability measure. All right. So now you talk about general measures. So now we know about probability measure, we know about Lebesgue measures. What is a general what, measure? All right. So a set function mu on a field f in omega is called a measure if it satisfies this condition. So now the space, we don't know the space you are working with, but we know that the measure, if you measure something, it should be positive. So for any a that belongs to f, for any a belonging to f, the measure of that set should lie between what, 0 and what, positive infinity. And we know that the measure of the empty space should be what, should be 0 as well. The third condition is that if a1, a2 up to infinity and they are the joint sequence of f set, this implies that if they belong to f and their union also belong to f, then if you defined the measure on their countable union is equal to their like the sum of their individual what, measures, the sum of their individual measures. This is called what, countable additivity. So we say that mu, which is a measure, is finite. If the whole space we are talking about, the measure of the whole space is what, is finite. And we say that mu is infinite. If the whole space, if you pick the whole space and you measure it and it's equal to infinity, then mu is what, infinite. Another property or another thing you can note about the general measure mu, we say that mu is sigma finite if there is a finite or countable sequence whereby this countable sequence belongs to f, such that the whole space can be written as the union of what, of these sets. Note, the a1, a2 need not be what, disjoint, such that if you pick any of the a keys or ai's, the measure of it is finite, then we say that mu is what, is sigma finite. So mu is not defined on the whole space, but is defined on the individual elements of what, of the omega, such that the measure of this individual element is what, is finite. So you can consider some examples of it here. Example 1 for sigma finite. So you can define the Lebesgue measure on R. So pick R to be 0 to what, 2. We can write R as what, 0 to 1, union what, 1 to 2. So if you pick any of these elements and take the measure on it, realize that it's 1, and 1 is what, a finite what, number. We can also consider the counting measure on the natural numbers. Note that the natural numbers can be written as the union of what, its individual what, elements. So in a counting measure, if you measure each of them, that the measure on the the measure of each individual is what, is 1, and this is what, is also what, is also finite. Okay, so this ends our lecture on Lebesgue measure, and we'll be taking our next lecture very soon. I hope you all have a good day. See you next time. Bye bye.